upward. So there we go.
We have an algorithm to make it go viral.
I don't know if that's a job anymore.
It won't be that interesting. I don't think so. So yes, thank you for having me here. Thank you for spending your Friday afternoon talking about quantitative methods. I know I can't think of a better way to do it, but so the title of my talk is my view on how I see my work and how it integrates into the work of other people. So to give you a sense of where that perspective came from, I did want to talk a bit about my academic history, as Steve said. So I was a graduate student in psychology at Kansas, and the program that I was accepted into was called the Experimental Psychology Program. And at the time, it was a blend of cognitive and quantitative psychology, and that was exactly what I was looking for. Soon after I got there, they split into separate programs, and I did my best to keep my feet planted firmly in both, and that's why I describe my PhD as cognitive and quantitative psychology. After that, I did a postdoc at Penn State focusing more on developmental methodology in the context of adulthood and aging. And my first job was at Nebraska, which is I was an undergraduate there, so you see a theme. I like to go places and then come back later. I was assistant professor until 2011, and at that point I took over, when I was tenured and promoted, I took over directorship of our cognitive program. For 1 year, we had a cognitive and quantitative program, or what I wanted to call the QUAG program, but they wouldn't let me. And unfortunately, that died when we left. So in 2014 then, until now, I have a split appointment at KU. So half of me is a tenured faculty member in an interdisciplinary program called the Child Language Doctoral Program. I teach quantitative methods. That's all I've ever taught. So that title sometimes throws people, which is why I wanted to explain what I do. The other half of me is the director of the Research Design and Analysis Unit in the Lifespan Institute, and we do grant support, analysis support, and that kind of thing for the lifespan researchers. So the research cycle then of quantitative methods. Arguably, quantitative methods, just like any other field, when you think research, you think innovation. You think new models, new estimators, new ways of doing business. The first task, though, after that part is the innovations are developed, is then to evaluate how they work. When do they work? When do they break? And what does that mean for how they're going to be used in practice? Then it's the time for implementation. And because of the types of positions that I've had, where I've been I've been one of the only quantitative people around in service roles, this is where I've spent most of my time doing, is what I would call implementation. And to me, that means two different things. It means translation, so making quantitative methods accessible to people from a broader audience, as well as adaptation, knowing when you need to tweak things to make it work for a particular situation. And when you find things don't work for a particular situation, that then spurs new innovation to develop new methods to solve that problem. And the cycle continues. I also have a common theme that I don't like to categorize myself as either measurement or statistics, but really I work at the intersection of both, or what another word I like to make up, measuristics. So yes, what do I do? So the quantitative stuff that I've done is primarily in longitudinal analysis, multi-level analysis, and also some latent variable measurement. I did write a book, and I'm happy that at least a few people are reading it because it took me 5 years. It was a labor of love. But most of what I've published in is actually many other areas, and this is the process of adaptation. A lot of aging stuff from my initial work as a postdoc. More recently, the collaborators that I'm publishing with are speech, language, hearing, and the world of ID. And when you look at this list and you wanted to think to yourself, what does this person do? And in fact, I had to answer that question at my interview in Kansas. I met with an associate dean who was flipping through my CV in front of me and saying, "You're all over the place." And I said, "I prefer the term interdisciplinary, sir." But the common thread here is that the work that I wasn't in charge of, all of these other areas were headed up by students. Because when a student takes my class and they want to bring the models they're learning into their own world, who am I to say no? So that's why I have so many areas. My students are the ones who are all over the place, and I'm very proud of that. So here's an example of one of those types of projects. So this is Alex Wasserman, who just defended his degree, and his advisor, Lisa Crockett, colleagues at UNL. And he was in a course where I was teaching generalized linear models, so models for non-normal outcomes, and we were talking about zero inflated outcomes. So when you have a count type of variable where you have a whole bunch of people who have a zero and then some sort of distribution after that, what do you do with that? And I was discussing two-part and hurdle models, and he raised his hand and said, "I think I can use this." So they do research in adolescent risk-taking, and one of the commonly used measures is the stoplight task. So the kids are told, you have to get to the party as fast as possible. And they have to negotiate a series of intersections in which they can decide whether or not they want to zoom on through. And if they do, they have a shorter delay but a better chance of a crash, or they can stop and they have a longer delay. So it's a risk-reward sort of situation. And in this variable, in this measure, what they end up using as a dependent variable is the mean latency to decide to brake. But then what do you do with the trials where they decided to go? And he said they treat them as missing data. And I said, no, that's like the definition of informative missing data, right? They didn't stop. So we fit, for his master's thesis that was published last year, a two-part latent variable measurement model, where one of the factors was the propensity to stop, which was the binary yes or no for each trial, and then for the trials in which they decided to brake, the latency with which they needed to do so. And what was interesting about this is that the variable that is typically missing data, that we made something out of, was the only one that mattered in predicting the outcome. The latency to brake didn't actually matter. So I like this example as something to where we can take a model that hasn't been used in a certain way and make new findings out of it. Another example comes from the idea of taking the things that you know in the world of ed measurement and bringing it to people who need it elsewhere. So the context of this is the PPVT, Picture P-Body Vocabulary Test. A sample item is over here. So you're given a vocabulary word, such as laughing, and you're asked to point to the picture that best describes that. So it's an incorrect or correct response. And like all good tests, the tests have continued to evolve to make sure that the vocabulary words are relevant and that they still mean the same things over time. And so this test was developed in, I think, 1969. It's undergone several revisions, and the most recent of which is coming out later this year. So at Kansas, a long-standing collaborator of mine and my current boss, Mabel Rice, she has given the PPVT to measure vocabulary in several longitudinal studies. And she was initially using this form RM, and when the new version 3 came out, she switched to that. But the new version 3 apparently used a different kind of norming sample, and so the scores she really didn't feel were comparable. So to hedge her bets, she started giving both of them instead. But the problem with this is that there's only 3 items in common. So I convinced her to collect another sample where she gives R and 3B, because that one has 121 common items. So we were able to put together a linking design in which we had overlapping items and overlapping people and do a concurrent calibration of all 459 unique items at the same time. This was tricky, and fortunately I had some help. A custom MCMC algorithm, and there's a scoring program now on my website written in SAS, so it uses proc MCMC, and researchers can insert their data and they get scores back no matter what version of the PPVT they got. And so this is really cool. It's the only way in which you can do longitudinal research in which the measure changes over time, is you have to have linking, of course. And so that was our next task, is then what can we do with these scale scores? Measure growth, just like she always wanted to. But we were able to do it in a latent rate as opposed to a scale-specific dependent score. So that's a little bit about implementation. Moving backwards in the circle, I'd like to tell you a little bit about the things that I do that I would consider evaluation. And really, this is the idea of doing simulation-type research to provide guidance to applied researchers on what to use and when. So most of the work that I've done in here is within the context of longitudinal studies, accelerated designs, intensive measurement designs, those sorts of things, trying to distinguish retest effects, practice effects that are short-term changes from more long-term changes. And there's one study in particular that I wanted to tell you about that I've done more recently, and this is the idea of systematically varying effects. So what is that? Well, let me give you an example. Let's say that you're doing a longitudinal intervention study. So you're looking to see whether or not your treatment group grows more than your control group over time. Very common thing in the world in which I live. So in multi-level modeling terms, we would say that we have level 1 occasions nested in level 2 persons, and the level 1 model for the outcome at time t and person I would look like this. Each person gets their own intercept, each person gets their own time slope, and those then become outcomes in level 2 to describe how each person gets their own. So it starts off with a common one, the fixed intercept and the fixed slope, which is the average for the control group in this case. And then we have the group difference in the intercept and the group difference in the slope. And this directly tells us what we want to know. This term right here is called a cross-level interaction. It's an interaction between group and time that says whether or not the treatment group grows more than the control. And no one in the world would argue with this model because of what lies after it, these U terms, which are known as random effects. So this is the idea that each person gets their own version of something. It's variance left over in the intercepts and in the person slopes that's unrelated to group. So when you're fitting these models, there's a stepwise process that's recommended. First, you test the fixed effect, then you test the random effect. And if that random effect is not significant, what comes next is up for debate. So is this version of the model okay? What if in this study, I didn't have a whole lot of people because longitudinal studies are hard to do, and I did not detect individual differences, a random effect in the time slopes? Are you going to tell me that I can't answer my research question because of that it's game over? I don't think so. To me, this is a reasonable compromise because I see it as just another option on a complexity continuum for how we would talk about level 1 effects such as time. On the left side here, this is what's known as a random effect. Everybody still needs their own after controlling for whatever covariates are in the model. On the right side, this is what I would call a systematically varying or non-randomly varying effect. It's not that everybody needs the same, and it's not that everybody needs a different one. It's that each group needs a different one, but within groups, everybody's the same. In other words, the time slope varies deterministically as a function of the predictors in the model, but not randomly otherwise. That seems perfectly plausible to me. And then fixed would be, no, everybody really gets the same. So to me, this is okay. To other people, this is not okay. And the reason that other people might object is because of the difference in how that group by time interaction would be tested in each model. There is a term here that's shown on the left that is only 0 when the slope variance is exactly 0. So it's missing over here when you don't have the slope variance in the model. So the standard error for the cross-level interaction will always be bigger to the extent that you have some kind of random slope variance. And so people worry about type 1 error when you're testing it with the wrong standard error. In small samples, you want to consider denominator degrees of freedom, so it's the idea that you have some kind of t-test instead of a z-test for the significance. And there's different ways of calculating denominator degrees of freedom based on each of these models too. And I've also had to argue with reviewers about this because they say, let me get this straight. You didn't find any differences in this slope, and now you're going to predict those non-differences? You're going to predict a constant? How does that work? And I say, well, the systematically varying, Radenbush, blah, blah, blah. More recently, a very commonly cited article, over 2,800 citations thus far, has suggested that no, systematically effects are decidedly not okay. And we all need to be fitting what they refer to as maximal models, which is that the default is random. Everything is random, always. And this is coming out of a world in which these are psycholinguistic types of studies where you have a set of items and a set of people and very few manipulated characteristics for the items and thus very few possible random effects. That's not my world. I live in a world where we might have somebody collecting multiple measures of multiple variables over days, within days, across people, and because there is such an intensive measurement, there's only maybe 20 people. If I have 10 time varying covariates, am I going to fit 10 sets of random effects in that covariance matrix and that's going to work on 20 people? Shaking your head, exactly. It's not going to go. So there has to be some way of letting the model be selected so that we keep the stuff we need and we don't have extra stuff that's going to make it break or blow up, as Jonathan said. That is how we talk in Kansas. So here's the question then. What happens in these small samples where you don't have a lot of power to detect that random slope variance? It's possible that if I say, nope, it's not significant, that's a type 2 error because I should have found it. If I make that type 2 error and I don't include it in my model, do I then have too high type 1 error? I find cross-level interactions that are significant just because of the messed up standard error. So that's the question then is, can we, through due diligence, solve this problem? So in designing this simulation, I did it a little bit differently than what is typically done on purpose. So in quantitative research, simulation design is typically analysis of variance type of design where you have very few factors. So for instance, in these types of analyses, you might manipulate intra-class correlation, and you might have a small one and a large one. You would then see what happened in your simulation based on those design conditions. So you would look at things like type 1 error or bias or whatnot, and how they differ as a function of whether that was in the small condition or the large condition. And why I decided not to pursue this route is because it's really difficult to choose the levels. How do you know how small is small? And it's difficult to generalize beyond. So what if you see a difference between small and large? At what point would that difference have been shown if you could actually plot out the curve? So we did it a different way. We decided to sample a range of each factor. So for instance, I sampled an interclass correlation from a uniform distribution, so block rectangle thing, ranging from 0.04 to 0.5. We then analyzed the results based on what actually happened, not what was supposed to have happened, and I'll explain that in just a second. And we did it this way because I feel like it provides a better approximation to what people do in the real world. When you collect data, you don't know what should have happened. You only know what you got. So let's go through the process of an analyst and try to make sense of what's going to happen, because that's how it's actually done. So the design then is using the same model that I showed you earlier. But critically, this group by time interaction, the cross-level interaction, is 0, always. So we're looking at type 1 error exclusively in this study. I picked sample sizes that we know are going to be underpowered for detecting random slope variances, between 10 and 50 level 2 units, or what would be people here, 3 to 10 level 1 units, or what would be occasions here. And then the values of the variance components in the model, we created a random intercept by sampling a range of intraclass correlations, as I said, so here's the formula for that. So given a fixed amount of variance, once you pick an ICC, you can figure out what these other two variances would be, where this is the between on the top and between plus within on the bottom. And we did the same thing to create random slope variances. So it's really hard to pick a plausible value of a random slope variance because it's variable specific and context specific. So rather than try to do that, I borrowed something that I found from Willett 1989, which hasn't gotten, I think, the press that it should have. He came up with something called slope reliability. And it's very much analogous to what you would think of reliability in a classical test theory sense. This is essentially true over total. So it's like, of the variance that's over time, how much of that is because people differ in how they change relative to the variation, this E-variance here, is around the lines. And then this is scaled as a function of how much information we know about time, as well as how many occasions there would be. And then we did, in terms of an analysis, the typical thing that you would do when testing variance components, you do a likelihood ratio test, and I used a mixture chi-square as I know I'm supposed to do. So once you have this slope reliability thing, you can calculate what the variance would have been that goes with it. So 3 results that I want to show you. What affects the power for detecting a significant random slope variance? So in other words, how likely is a type 2 error in these types of small samples in which I live? Unsurprisingly, slope reliability mattered most. It's an effect size. It describes how big your variance is. And the more reliability you have, the better chance you have of finding it. So this is power on the y-axis here. In terms of how sample size interacted with slope reliability, though, we found a different pattern than what I would have anticipated. So this plot on the bottom here, the y-axis is the correlation between sample size and power. So the extent to which more people are better as a function of slope reliability on the x-axis. And more people aren't always better. More people start to get better, more help improve your power, once your slope reliability is big enough to be found, and after a point where it's so big, it doesn't matter how many people you have. And this is exactly the kind of nonlinear association that I never would have seen had I just picked a few arbitrarily chosen values on this continuum. The bottom 2 lines here is the level 1 sample size, which in this case is number of occasions, and that didn't matter a whole lot, which is actually contrary to what some other folks have found in this type of context. These are empirical power curves, so showing the effects of sample size more generally. The take home here, 10 people are not enough. That's this little sad line over here that never quite gets up to power of 0.8. And neither are 3 occasions. So I teach longitudinal, and I tell them, the minimum you need to basically participate in this class is 3 occasions. If you already only have 2, ANOVA is fine, right? And 3 really isn't enough. This is like, the rest of these are okay, but 3 is just sort of a disaster. So second then, given the decision that we make, so we test the random slope variance, we decide whether or not it's significant, which means keep it, or non-significant, which means we should be able to drop it. Given that scenario and that decision, how often do we make a type 1 error? And in small samples, it's better to use residual maximum likelihood rather than regular flavor maximum likelihood because the latter underestimates variance components. And there's also corrections for degrees of freedom. And so I'm using sort of the best case scenario in terms of making all of those choices, which is what an analyst hopefully would do as well. So 26% of the time, we found the random slope variance to be significant in these replications, in which case the decision is unequivocal. Keep it. When you keep the random slope as you should, type 1 error rates are 5%, exactly where they should be given the alpha that we used. When you don't keep a significant random slope, bad things happen. That's this bar right here. It's 16% type 1 error. But the interesting thing about this is the other side. So this is a well-known result, which is why people say test the random slope first before you test the cross-level interaction. So over here, 74% of the time, the slope variance was not significant, and in theory, I should have been able to get rid of it. Not exactly. If I play it conservative, that's the green line right here. Type 1 error is 4% if I keep an unnecessary random slope in the model. That's the maximal models argument. But if I get rid of it, type 1 error is just a little too high, 3% avoidable errors, basically based on model selection. So then the question is, how did they sneak in there? And the only logical conclusion, I think, is that these are the type 2 errors that I was worried about for the random slope variance. It was big enough to cause a problem in the standard error, but not big enough to be detected as significant. So what do we do about it? Well, I'd like to propose, rather than looking at just significance, that we consider effect size. I know that's very novel, but it hasn't been applied in this context. So I developed a new criterion based on slope reliability. I can give you the background for how we came up with that number if you want. But basically, I propose keeping any random slope variance where the slope reliability is greater than 20%. So it's significant, or it's a big enough effect that you need to worry about. So this is what happens when trying to apply that decision rule. I'm going to show you plots where the different lines are for different estimators and the panels here are for different methods of degrees of freedom. The gray dotted line is the reference for what type 1 error should be. And so if you do the traditional procedure, likelihood ratio test of alpha equals 0.05, type 1 errors are 4 to 5% higher than they should be. Not a whole lot, but enough to make me squishy, as I would say. What about just a more conservative, a less conservative likelihood ratio test? How about let's bump the alpha up? Doesn't really help. But this one works. Across every degrees of freedom version and estimator, type 1 error rates are right where they should be. And that's because we got rid of the trials that were messing up the error rate. They're now in the other set of replications where we would have decided to keep the slope. So my conclusion is that systematically varying effects can be okay. The trick is that the analyst has to do their due diligence. And that involves two things: keeping a random slope variance that's significant or crosses this effect size threshold, and keeping it in the model no matter what. So we looked at what happened after the predictor was included, and if it became non-significant, could you get rid of it? No. Only when it's exactly 0 were type 1 error rates okay. So that brings us back up to the top then, innovation. And most people think about innovation as new models, but I also like to think of it as new combinations of models, putting things together in a way that hasn't been done yet to see if the whole is greater than the sum of the parts. So this work is actually taking me back to the future. This is building on some things I did at Kansas and at Penn State. And as a student in cognitive, I became very aware of the dichotomy in how we think about research design plays into what we do with our studies. So at Kansas, it was a very strong experimental tradition in their cognitive program. We did very controlled studies. But then at Penn State, it was a very different individual differences style, and they were all about psychometric measures. And these two approaches couldn't be more different. The goal of an experimental study is to have lots and lots of trials that are tweaked very carefully to get at the hidden architecture of the brain or of attention. It consists of usually not very many people, but a whole lot of trials, and you're trying to measure one thing. Over in psychometric measures, so in the context, say, of cognitive aging, things like the digit symbol substitution task or Wisconsin card sort, that kind of stuff is what I'm talking about. The goal is to measure individual differences in fuzzy things like cognition, cognitive people would say that's one thing. Yep. They generally give very few items, and the items are not all that well constructed. And they're trying to measure multiple things, sort of each one very coarsely. Where they start to get somewhat similar, though, is in the approaches that people use to quantify individual differences. You can do so with an observed variable, in which case, like in an experimental design, you might compute mean response time for a particular condition or mean accuracy. And the analog on the psychometric side would be classical test theory, where you have the sum score, something like that. But each of these can be made stronger by bringing in the influence of latent variables. And this is called multi-level modeling in the context of experimental studies, or mixed effects modeling, where you would represent individual differences in ability with a random intercept. It's called confirmatory factor analysis, or item response theory, depending on the type of outcome in this world, where that same random intercept is called a factor score, or a theta, or a trait estimate. So in trying to reconcile these two traditions, as a postdoc, I got a chance to read this book, which is Explanatory Item Response Models by DeBach and Wilson. And it was really hard for me to read at the time, to be honest, but I'm glad I did, because it totally changed the way that I was thinking about this. And I thought, why don't we put it together? And this is the modeling approach that allows it to happen. So we can take the fine-grained task decomposition that we would do in an experimental setting, and we can use the same sorts of rigorous latent trait models that are much more common in psychometrics, and we put them together. So this is a line of research that the goal is to create measures of cognition that are both theoretically solid and psychometrically defendable. And the area in specific that I tried to do this in was visual attention, which is the first type of research that I got into in grad school. And I picked that because there are no psychometric measures of visual attention. I think there's only one that I can think of, and it's kind of sketchy. These types of abilities, though, visual attention types abilities, are really important, though, in the context of cognitive aging, as one, when you think about older adults and how to discern who's a safe driver, who's still capable of living independently. Those are the kinds of things where a measure of attention could be used. We know that visual attention is a contributor in people becoming unsafe drivers. And because visual search has been studied to death by experimentalists, we understand task difficulty really well, and it provides a nice simple recipe for item creation. So this is work that was funded by NIH, an R21 that I had at Nebraska. This is my collaborator who ran the lab, Joan McDowd, and this is her Greyhawk lab, where it was at the time. So you get it? This is Greyhawks. It's an aging lab? No? Yeah, she told me that she purposefully picked like a Jayhawk. This is from the 1930s or something that just like looked a little old to her, and so this was her mascot. Her license plate said Greyhawk on it too. But then she left for the University of Missouri, Kansas City. So the goals of the project then were to examine the dimensionality of visual attention. If I give you a whole bunch of tasks, do they converge onto the same type of trait? And also to see the extent to which the same factors could predict difficulty across traits. And so let me show you the types of tasks that we used. So this is what I would call a context-free task. This is the kind of thing that you would find in an experimental study for visual attention. So on the left here, there's only one T that's sideways. Is its top on the left or the right? Yeah, it's right here. And over here, there's only one H. Is it red or green? So these tasks are used because you can control basically every aspect of the display and very carefully manipulate things, but it's hard to argue that they're ecologically valid. So we created two new tasks that were designed to measure the same thing in a more realistic context. Web page search. You're to find one link that's either to the Med Center or the Greyhawk lab. Takes a while, right? Yeah, it's this one in the middle here. Or grocery shelf. You open your pantry, you try to find what's for dinner. It's either going to be corn or carrots. Which one are you having tonight? This is a tricky one. There's the corn right here. Yeah. Touche. Touche. Well, I grew up in Missouri and part of Iowa, and we did have corn in a can at my house. So.
Not this time of year.
Not this time of year. Yes, agreed. I also do love corn on the cob. So these are the types of tasks then, 2 basic search tasks and 2 more applied tasks, and they were constructed in a parallel manner. So in previous studies, people use response time. How quickly can you find these things? That turns out to work not very well when you're measuring older adults because they want to be really sure of their answer. And so they take longer to decide that they're sure than to just find it. And so we used accuracy as the outcome and manipulated presentation time. So we made the task harder by not giving people as much time to search the displays. And to keep the sensitivity of the task, we had 3 different presentation times. Everybody, younger and older adults, got the medium time. Only the younger adults got the shorter time, and only the older adults got the longer time. So they were linked on medium, but each group got another set of trials that would hopefully be more useful to indicate their abilities. And then we manipulated the typical stuff, location, number of distractors, all of that kind of stuff. And everybody got 2 out of 3 test forms, which was counterbalanced. So in thinking about how do we model ability from this kind of task, or the idea of measuristics, if you think about it from a psychometric perspective, well, one possibility is what we call the 1PL, or the Roche model, right? We have a person ability, which is theta, and we have item difficulty here, and we use a logit link because we're modeling accuracy. That same model I would call a multi-level model. It's a generalized version in which now I have a random intercept, which is the same thing as theta, and I've replaced this idea of item difficulty with a series of indicators. So these are dummy codes that distinguish each item. Because it's plus signs, it's item easiness instead of difficulty, but it's exactly the same. So this model works really well when you have specific items and you want to have an item-specific difficulty. What it doesn't allow us to do is to predict why some items are more difficult than others with features of those items. To do that, we have to expand the model, and this is the explanatory item response model, or what I would call a multi-level model with cross-random effects at level 2. The idea is that we still have person differences in ability here as a random intercept, but now we also have random differences in item difficulty. It's a variance to be predicted. So we can put in predictors that pertain to why some items are more difficult than others and see this variance go down. And we can also put in person predictors for why some people are more able than others and see this variance go down. So this type of modeling framework allows us to do a lot more things than would have been possible otherwise. I don't have time to talk about all of the item predictor stuff. I figured I would focus on reliability instead. So how did we do? How reliably can we measure something with this type of task? Turns out pretty well. As you might anticipate, test information is pretty good when you have 225 items. To convert test information to something easier to understand, this is reliability, and it's uniformly high across the spectrum of the trait. I note that in experimental studies, you never see reliability reported. They will report, mean response time or mean accuracy for this condition, but never reliability. Whereas on the other side, the psychometric side, you have to report reliability or no one will believe you. So in looking at these levels of reliability, I thought, do we really need 225 items? Because that's a lot. Can you imagine sitting there, finding the H 225 times? Right? This is what we make undergraduates do all the time in psychology, but regular people who aren't trapped by the intro psych pool don't want anything to do with that. So can we get rid of some of the items but still keep the reliability? And the answer to this depends on how we're thinking about a score. If I'm using a sum score or mean accuracy, something like that, where the score is tied to the items, then no, because each score is only comparable if it's the exact same set of items. But if you're working with models in which you're estimating parameters for both ability and item difficulty, then yeah, we can do this. And so this is a follow-up study that we did at the University of Nebraska. It's adaptive testing cognitive style, or cognitive style, as it were. And so fortunately, I had an in-house psychometrician who could write algorithms for me. Those are handy to have, let me tell you. And he wrote an adaptive algorithm that selected the next item to be administered in these search tasks using item difficulty that was calibrated from the previous study, but then we used presentation time to fill in the gaps. So if the next item difficulty was, I need a 1.7, and all I had was 1.8. Well, it's not quite. That's I only have so many items. I'm going to show it for less time, and that's going to make it easier. So use presentation time to tweak it and fill in the gaps. And Lindsay Wiley was the one who helped run the study and recruit everybody, so she has my eternal gratitude for that as well. So here's what happens. So this is a new sample of 34 older adults. They completed 50 adaptive trials using this algorithm. So these are panels for each of my tasks. This is standard error per trial on the top here. And so you see it come down right away, so standard error for the person trait. This is change in standard error as a function of trial. And what you can see is that it flattens out. It gets to be about as good as it's going to be after 15 trials. 15. Here are the ability trajectories. So ability per trial on the top and change in ability on the bottom so that you can see the variance start to shrink. And after about 15 trials, all of the changes are within one standard error. So it takes 15, not 225. And you get as good a measurement as you would have had. We had a sample of younger adults, and because they are more captive, we gave them 150 trials, just to see, make sure that 50 wasn't enough. Same pattern. Standard error came down after about 15 trials. Ability settled right into where it was supposed to be after 15 trials. But these trajectories also highlight another issue. What happens when the undergraduate in your study loses their will to live during your search task? That's these guys right here. So you think about measurement, more is better, right? More items, more reliability. Not if they hate it. So to look at this a little further, I plotted the mean ability levels taken at trial 50 and those taken at trial 150. And here's what it was for the older adults. And in every case, we see what I would call the will to live effect. The younger adults look worse at the end of the test than they did partway through. So this would be another argument for why you don't want 225 trials. You want to be able to keep people engaged in the task. So unfortunately, I haven't had a chance to pursue this research much further after I left Nebraska. But if any of you know, say, cognitive people who would like to come talk to me, I would love to be interested in new collaborations. So up to this point, I've been talking exclusively about research, but my passion is teaching, and it turns out that a lot of these same ideas apply when you talk about the teaching of quantitative methods as well. And here, I'd like to think that I'm trying to be as innovative as possible as well. So who I've taught in my career, no matter where I've been, has PhD students exclusively. They come from a series of areas throughout the social sciences, as you saw by my Vita that was all over the place. And the 3 courses that I teach currently, I have a 2-semester sequence that's of multi-level models for longitudinal data in the fall, and then the advanced course that follows it that expands on that into other kinds of multi-level designs and multivariate and that kind of stuff. I also have what I think is an interesting version of a measurement course, which actually originated with Jonathan as well. He had this sort of idea, and now we're at the point where we trade off who teaches it. But it combines measurement and structural equation modeling specifically for people who are not in educational measurement. So people in social psychology or clinical psychology who need to understand scale development and how to do modeling with it. So it combines confirmatory factor analysis, item response theory under one umbrella. I show them how these things are related, and then we show how to build structural models into the SEM part that are based on either one. So I have a lot of fun with those courses. The thing that I would like to spend just a couple minutes on that we have left here is what I do in terms of assessment, which is the idea of online homework. So before I get into that, what I used to do is have relatively small classes, maybe 12 to 15 students, and I would give them data analytic assignments, and I would make them write up a results section and turn it in. And I spent hours and hours and hours grading these things and trying to give individual feedback. And invariably what would happen is that they screw something up at step 2, and so everything after that is wrong, which is a waste of time for both me and them to continue on, or their writing is such that they've never learned how to write about these models, and when they write something, I can't tell if they don't understand the concept or they just didn't know how to tell me that. So to solve these problems, beginning in 2012, we developed an online homework system that is designed to clone us. So what we do is use each student's ID number as a random seed. Each student gets their own data set. That way there's no borrowing. And there's two different kinds of questions. Computational questions get immediate feedback, and we have results types questions that get delayed feedback. So I have I can do a demo for anyone who's interested later, but I'll just show you what it looks like here. So these are the types of computational questions. So each of these is a number that takes input. If it's right, it turns green. If it's wrong, it turns red. And you can try as many times as it takes to make it green. So the first question here, so given the story and given your data, enter your first model's -2 log likelihood. Now I use this because this is a unique number that tells me if they have the right model. I then zero in on what else I want them to pull out of the analysis. Some of these things are for checking whether or not they have the right model, and some of these are things that would be reported. So once they have all of the numbers green, they go on to complete a results section. And if you remember what Mad Libs looked like, I know I'm probably dating myself, right, with the fill in the blank, that's what this is. So each section of text that you see that's either red or green, that was a drop-down menu where they had to select an interpretation. So things like significant or not, main effect or simple main effect. Does this significance test mean you have mean differences or a variance? Those are the kinds of things that people screw up. And so I'm giving them the structure in which to write a results section. And they submit it for a grade. After they submit it, their answers turn green if they're right, turn red if they're wrong, and the right answer is given for every incorrect answer so they see what it should have been. And all of the numbers that they found already here get populated into their spots so that they can see what the result what they're describing would have been, and they know where they got it from up here. So this has allowed us to have way more people in a class. I get to spend my time helping them rather than grading. So I do office hours in a computer lab, and a lot of the students just take time out of their schedule to work on their homework in the lab. So if they get stuck on something, I go help them, and then they keep moving, and I go to the next person who's stuck, and I help them, and we keep moving. And so it's a lot more time interacting with them or saying, why is this still red, and going over the work that they're doing, rather than after they turn it in when it's too late. And the other nice thing about this is that I believe that it teaches them how to write results sections without me having to do it. These are templates that they can fill in later. Results sections are usually highly formulaic, and so I'm hoping that they now have an example to use anytime they need to run a particular type of model as to how it would be talked about in a publication. So, wrapping up here, what do I want to do in the future? Teaching. This homework system, I would love the chance to try and make it a thing, make it available for broader distribution. Right now, it is a very kludgy SAS program that runs all of this that only I could ever wade through. Jonathan has a version in R that he gets to wade through, but it's lines and lines and lines and lines. It is not user-friendly. I don't know enough about computer programming or any of those sorts of interfaces, but again, looking for opportunities to be able to make this a thing, because I think it could be useful for lots of different types of teaching where you don't need to be doing the grading. You should be focusing on other things. I'd love the chance to develop new methods courses. Right now, I don't get a chance to teach as much as I'd like to, so I would welcome that change. And then in terms of research, where I see my stuff going is really more towards this evaluation side. I have a lot of questions that I haven't had the chance to answer, and most of those broadly construed are about what happens when the real world of small samples meets this idea of measuristics. So when you want to do something like examine growth in a latent trait, can you do it all at once when you only have 20 people? It's not going to go well. So when you can't make the right choice, what can you do that's least wrong with what you have? Those are the types of questions that I'm interested in. And here's just a couple examples of things that I've been asked about where I didn't have a good answer and it bothered me. And I wanted to do more research to figure out what I should tell people. So that is it. Thank you very much for your time and attention, and I'm happy to take questions.
Several minutes left for questions.
Yes, sir.
Yes.
In your analysis, choosing the right random slope structure in mixed models, at least what you showed us today, it looked like you were basically locking the fixed effects at 0 and looking for type 1 errors.
Yes.
But the criticism on Barr's proposal is that it's under-conservative, or it's over-conservative. So if you tried the converse, where you put a fixed effect in and see what your power looks like?
A little bit. And yes, I do find a power improvement when you're not fitting maximal models. I haven't had a chance to do much with it, but I played around a little bit. Yeah, that's the next logical step. I just wanted to see the type 1 error rates because that's the criticism that it seems like they were making most prominently.
Well, everybody's conservative these days. We find an increase in power when you use a selection procedure.
It doesn't surprise me.
But we also don't find, and I'm surprised by your finding, the increase in type 1 error. Actually, if you use a different model selection, it seems like we can hold it constant. But I don't know if we're working in the same space as you are.
It may not be. Yeah, I'm applying this to small sample longitudinal types of studies, and so all the parameters were sort of designed to mimic that situation. I think it's a little bit different in those models where there's items and people and that kind of thing.
Right. Yeah, ours are cross-ranking effects models, so
yeah,
it's an interesting concept.
Yeah, those have their own estimation challenges. So I wouldn't surprise that some of this is because of it's not a crossed model, just a nested.
Although that was the area Barb was working in when he proposed keeping it maximal. So
true.
I think it's an interesting contrast. Again, a collision of worlds you were talking about.
Yes.
Other questions, comments?
I got one. Excuse me. This is related to the teaching part of your talk. In the second of the two courses that you were talking about, that was something that you said was accessible to a variety of different disciplinary focuses.
The measurement course.
Can you talk a little bit about the prerequisite background knowledge with respect to statistics or measurement for a course like that?
Yes, regression.
Okay.
Ideally, I would have liked you to have seen maximum likelihood before. Like a sort of a modern take on multivariate is an ideal prerequisite, but that gets taught inconsistently where we are. And so I just say regression because the way that I teach it is as a linear model. CFA is to linear regression as IRT is to logistic regression, and so if you understand a linear model, I can go from there. Say, oh wait, by the way, X is latent, but otherwise it's the same.
And then, can you say a little bit about the diversity of students that you work with in that course?
All over. People from communication studies, business, education, psychology, clinical psychology. I've had linguistics students before. I've had, trying to think of, ed leadership, curriculum and teaching. Yeah, all over campus. So ideally that would be a 2-semester course as well. I just don't have room in my schedule for it to do it that way. Yes, sir.
Back to the longitudinal example. Did you run into convergence issues with any of that with the small sample sizes?
There were, I think maybe, I want to say 1,200 replications or so that I ended up kicking out because they didn't converge in one of the models or the random intercept went to 0. Interestingly, when we submitted this paper for review, the editor wanted me to try no bound, the idea of estimating unconstrained variances, and that made it worse. All of the things that previously converged did not converge in no bound. So I would not recommend that as a strategy, by the way.
What did you tell the editor?
We tried it, see tables 5 and 6, it didn't work. She did not like that answer.
Well, let's thank Lisa again.